Hey everybody, welcome back to Cash Casting. My name is Akash, and with me is Rahul. Today we're going to explain to you the basics of Archimedes' principle with applications to Newton's second law. Then we'll be taking you through some examples that can hopefully provide a better understanding of the physics behind objects floating and sinking. Now let's start off with the fundamentals of Archimedes' principle. Now, as you can see, it's essentially showing a relation between the buoyant force of an object and the weight of displacement of a fluid. Now, you might be asking, what exactly is the buoyant force? In this situation, you can kind of imagine it like a normal force of water. The force that water is pushing back against the object. And this applies with Newton's third law, which says that an object exerts an equal and opposite force, sort of like how the normal force can equal mg. And this can be seen when we drop things in water. Now let me get my Minecraft Roblox simulator here. And as you can see, there are two blocks, a wooden block and a brick block, and each have the same mass. And as a matter of fact, we can even show the gravity and buoyancy forces acting on the object. And at the moment, neither of them have a buoyancy force because they're not in water. But what if I were to drop this in water? As you can see, the brick block, despite having a smaller volume, has a larger density, so therefore it sinks. And the wooden block, even though its volume is larger, has less density overall, allowing it to float. And we can even see this if they have the same volume. Now in this case they have different masses, but their volume is going to be the same. And if we drop them, the same result occurs because the brick block has larger density than water, making it sink. Now at this point, I'm going to pass the burden, stick, to Rahul here, who is going to help us get a more college level understanding of this topic and do an example problem along with it. Rahul?
Thanks, Akash. To start off, there are three main formulas necessary to solve an Archimedes principle problem. So this may seem kind of familiar because, well, it is. We're doing the same thing Akash just explained, except with the values, trying to find the net force acting on the object. So first, you gotta find the weight of the object itself, which is self-explanatory, mg, and then subtract the buoyancy force from it, and that's your net force, because they're acting in opposite directions. And throughout this time, you may have always been wondered how to calculate the buoyancy force, so let's take a look at that. You first need to find the density of the fluid, which you can look up after this video. Then you multiply that by the volume of the displaced fluid, basically the part of the object that is submerged. And again, multiply by g, because remember, there's still a gravity force. And lastly, this is a somewhat obvious representation, but to find the fraction of the volume of the object that is submerged, simply take the part of the object submerged and divide it by the total volume of the body of water. And that is now your ratio of fluid displacement. These three formulas can give us a better understanding of what happens to the two vertical forces as the density of the liquid, mass of the object, and volume of the objects all change in various ways. For example, if the density of the liquid goes up, the buoyant force applied by the liquid on the object increases, seen in the second formula. So now, on to some practice problems. The problem states that Akash was playing with his toys in the bathtub. A rubber duck of volume 0.5 meters cubed and a mass of 0.25 kilograms is gently placed into the filled bathtub, which is filled with water. Calculate the net force and percentage of volume of the duck that is submerged. So to do this, we obviously need to use the formula for the net force, which is mg minus B. And we know M and G, but we need to find B. So right here, we do 1 times 9.8 minus B. And on the other side, we have the formula for B, the buoyant force, which is the density of the liquid times the volume of the body submerged, or the object submerged, times the gravity. Continuing, we don't know the density, so we set that equal to the mass of the object divided by the volume of the object. And we have 0.5. And for G, that's 9.8, as usual. And for the volume of the body submerged, we need to do some math right here. And that also gives us the percent of the body that's submerged, which is 50%, or 0.5. And V of F is equal to 0.25 meters cubed. We plug that in, and B is equal to 1.225 newtons. Now we use B and plug it back into the original equation to find the net force, which is 9.8 minus 1.225, and that is equal to 8.58 newtons.
Now that we have all our concepts down, let's put it to the test. Now, water we know has a density of 1, and my prediction is I am less dense than water, therefore I should float. But let's first see how deep this water is.
Bro, it's fine. You're less dense than water. You'll float. It's all good. It's all good.
I'm not so sure anymore.
It's all good. It's all good.